When engineers run into a bottleneck, I feel like the instinct is almost always, well, let's just build a workaround.
Right. Yeah. You optimize the code or you just throw more processing power at it.
Exactly. Add more memory, buy a bigger server. But what happens when that bottleneck isn't a hardware limitation or, even poorly written software?
What if it's the math itself?
Yeah. What if the bottleneck is a fundamental law of mathematics? Like a literal mathematical impossibility that's been standing in our way for, gosh, over 200 years.
Well, in that case, you really can't build a workaround.
Right.
You have to build a totally different kind of engine, one that takes that mathematical dead end and basically uses raw, relentless computational brute force to shatter it millions of times a second.
And that exact collision between pure mathematical theory and bare metal parallel computing is exactly what we're exploring today. Welcome to the deep dive.
Glad to be here.
We've been looking through some really fascinating sources today. We have this visual architecture teardown called Parallel Polynomial Root Finding.pdf and a presentation deck, ginger-slides.pdf. Both of them focus on this highly specialized C++ library called ginger-pre.
Yeah, and it is a library engineered to solve one very specific, massive bottleneck in modern computing: parallel polynomial root finding.
Okay, let's unpack this, because obviously everyone listening knows why finding the roots of a polynomial matters. We're not talking about like high school algebra homework here.
No, definitely not.
In the professional realm, whether you're dealing with quantum mechanics or modeling signal processing paths,
Time series statistics.
right, time series statistics, or analyzing the stability of complex physical engineering systems like aerospace dynamics, you are relying entirely on finding the roots of massive polynomials. It's the absolute foundation of all these fields.
It is. It's really the hidden engine running the modern scientific stack. The problem for us isn't why we do it. The problem is the scale.
The sheer size of it.
Exactly. Modern applications don't need the roots of a simple quadratic equation. They need the roots of a degree 100 or, even a degree 500 polynomial.
Wow.
And they need those roots with extreme precision, evaluated in real time across thousands of incoming data streams.
Which brings us right to that 200-year-old mathematical wall I mentioned earlier. So we all learn the quadratic formula, and maybe you even know there are closed-form algebraic formulas for cubic and quartic polynomials, right?
Right, degrees 3 and 4.
Yeah, you plug the coefficients in and you get the exact roots out. Neat and tidy. So remind us, why can't we just scale those algebraic formulas up to a degree 100 polynomial? Like, why doesn't a degree 100 formula exist?
Well, it all comes down to a discovery made back in 1824.
1824.
Yeah, the Abel-Ruffini theorem. And this wasn't just a case of, we just haven't found the formula yet.
Right.
Niels Henrik Abel actually mathematically proved, that no general closed-form algebraic solution can exist for polynomials of degree 5 or higher.
That is just wild to think about.
It's a hard, mathematically proven dead end. You simply cannot just plug numbers into an equation and get the roots once you hit degree 5.
So what does this all mean practically? I mean, it's not a lack of human ingenuity. It's the universe literally saying there is no direct path from A to B here. So if the math explicitly forbids a direct formula, how on earth are we finding the roots for these massive polynomials in our engineering simulations?
Well, it forces us to rely on numerical iteration.
Okay.
Because we can't jump straight to the exact answer. We have to use these numerical iteration engines to basically guess.
You just guess.
Essentially, yeah.
Huh?
We make a highly educated guess about where the root might be. We run that guess through the polynomial, calculate the slope of the curve at that exact point.
Which is like a Newton step. Right.
Exactly, a Newton step.
Yeah.
And then we use that slope to adjust our guess and try again.
So we're just inching closer and closer to the true answer.
Precisely. But here's the catch. For a degree 100 polynomial, especially dealing with complex numbers, you might have to evaluate, check, and adjust millions of times across all the different roots before you converge on the precise answers.
Millions of times.
Yeah. That 1824 theorem is the entire reason we need immense raw computational power just to do what seems like basic algebra.
Right, which totally sets the stage for the actual software design of ginger-cpp. Because if we are forced to guess and check millions of times per second, we had better be unbelievably efficient about it.
Oh, absolutely.
You can't just throw a massive polynomial at a CPU and evaluate it the naive way. Like if I have x to the power of 100 and I just multiply x by itself 100 times and then do x to the 99th and so on, I mean, that has to be devastating to the processor.
It is computationally ruinous. Evaluating a polynomial the naive way requires a number of multiplications that's proportional to the square of the degree,
Right.
what computer scientists call O of n squared complexity. So as the polynomial gets larger, the computational cost just explodes exponentially.
It just spirals out of control.
Completely. So before you can even think about multi-threading or parallel execution, you have to strip away that computational waste. And that is done using Horner's method.
Okay, yes. Horner's method. I was looking at the visual breakdown of this in the documentation, and the way it transforms the math is brilliant. If I can try an analogy here, it's sort of like a set of Russian nesting dolls.
Okay, I like that.
Because with the naive approach, you're essentially building 50 separate wooden dolls completely from scratch. You build the sex to the third doll, then you start over and build the X to the fourth doll.
Right, lots of redundant work.
Exactly. But with Horner's method, you mathematically factor out the X's to create this nested multiplication chain.
Yes, exactly. You restructure the polynomial so it looks like a series of nested parentheses. You take the highest coefficient, multiply by x, add the next coefficient, multiply the whole thing by x, add the next, and so on.
So you're just putting one doll inside the next. You use the result of the inner calculation to feed the outer one straight down the line.
And what's fascinating here is that by doing that, you reduce the number of multiplications from O of n squared down to just O of n.
Wow.
It becomes a linear, hyper-efficient operation. And what makes ginger-cpp so effective is how deeply this optimization is embedded directly into the library. It uses standard vectors in C++ to store the coefficients, but it iterates through them in strict descending order.
Wait, why does descending order matter so much to the hardware?
Because CPUs absolutely love predictable, contiguous memory access. By structuring the math to flow in one straight descending line through the memory addresses, the CPU cache can prefetch the data perfectly.
Oh, I see.
Yeah, there are no cache misses. This mathematical streamlining is the absolute prerequisite before any parallel computing can even begin. You have to build a lightweight, perfectly balanced chassis before you drop in the massive engine.
That perfectly sets up the engine itself then. So we've optimized the evaluation part, but we still have to actually hunt down the roots. The architecture docs make it clear there isn't just one algorithm doing this, right?
Right.
Ginger-cpp uses a dual engine routing system. So how does it know which engine to use?
It analyzes the coefficients of your target polynomial first, because no single mathematical approach handles all profiles efficiently. So the library routes the execution based on its mathematical properties to whatever will be fastest.
Okay.
The primary engine, the real heavy lifter, is the Aberth-Ehrlich method.
Let's dive into the Aberth engine. The docs say this is used for general polynomials with complex roots, and it uses something called simultaneous global iteration.
Yes.
So instead of finding one root, dividing it out, and then looking for the next one, it tries to find all the roots at the exact same time.
It does. It unleashes this massive swarm of guesses across the complex plane all at once.
The project visualization has a fantastic electrostatic analogy for how this swarm operates, which really helped me grasp it. So, picture a 2D grid representing the complex plane.
Yeah.
The true hidden roots of the polynomial are like fixed positive holes on this grid. And our initial guesses are dropped onto the grid as movable negative charges. As the algorithm runs those Newton steps we talked about, calculating the slope, these negative charges are like magnetically drawn toward the positive holes.
It's a beautiful way to visualize it.
It's not
But
bad.
there's a massive danger inherent to this global approach.
Right.
Think about the physics of what you just described. What happens if 2 or 3 of your negative charges happen to be located near each other, and they are all drawn to the exact same positive hole?
Oh, they would just crash into each other. They'd all converge on a single root, and you'd completely miss the other roots you were supposed to be finding.
Exactly. In standard iteration, that overlap is a fatal flaw. You just get redundant answers.
Yeah.
So to make simultaneous iteration actually work, ginger-cpp applies the Wilkinson correction.
What does the Wilkinson correction actually do to the math, though?
It introduces a fractional summation term into the denominator of the step calculation. But going back to your physics analogy, what it essentially does is turn your negative charges into magnets that repel each other.
Oh, wow. So when one approximation gets close to finding a root, it emits a repulsion wave.
Precisely. As an approximation homes in on a root, its mathematical charge begins to cancel out the pull of that specific root for all the other threads. It creates a repulsive force that actively pushes the other guesses away.
Forcing them to alter their trajectories and seek out the remaining unoccupied roots. That is incredibly clever.
It really is.
But for that repulsion to work efficiently, you can't just drop your initial guesses randomly on the grid ray. Like if you drop them all on one side of the board, the repulsion waves would just scatter them into deep space.
That is why initialization is so critical. You have to avoid what we call symmetry traps.
Symmetry trap.
Yeah, where guesses get locked in endless geometric loops. So the library uses the circle method. It calculates the mathematical center of gravity of the polynomial, determines a safe orbital radius, and then distributes the initial complex values perfectly evenly along the circumference of a circle surrounding the entire target space.
So they are collapsing inward from all sides simultaneously.
Yes. And because they are perfectly distributed and repelling each other to avoid those redundant roots, the Abirth method achieves rapid quadratic convergence. The guesses accelerate toward the true roots, hitting tolerance thresholds down to 10 to the negative 14th incredibly fast.
Hitting 14 decimal places of precision simultaneously is staggering. But there's a heavy computational tax for Abirth, isn't there? It requires complex number arithmetic. Even if your polynomial only has real numbers, Abirth forces the system to calculate using imaginary planes.
And complex math is a massive burden on a CPU. A single complex multiplication requires 4 separate floating point multiplications and 2 additions.
Wow.
So if your polynomial only has real coefficients, forcing the CPU into the complex plane is a massive waste of clock cycles.
Which triggers the secondary routing engine. If the library detects real coefficients, it switches away from Abirth and fires up Bairstow's method.
Correct. Bairstow's method is a deflation-based algorithm. Instead of hunting for individual complex roots, it extracts quadratic factors.
Okay, chunks of the polynomial that look like x squared minus rx minus s.
Right. And by staying entirely within the bounds of real numbers, it completely sidesteps the massive performance drain of complex arithmetic.
Okay, I have to stop you here though, because when I was reading the architecture docs, I was completely lost on how Bairstow fits into a multi-core library.
Oh, the concurrency problem.
Yeah. Because standard deflation is strictly sequential. You extract a quadratic factor, you divide it out to shrink the polynomial, and then you run the method again on the smaller polynomial. Sequential implies a single file line. You can't parallelize a single file line.
No, you can't.
So how are they running this across multiple threads? Doesn't that totally kill the ability to run things in parallel?
You have just hit on one of the most elegant solutions in the entire library. You're absolutely right. Standard deflation is sequential, which usually causes a total bottleneck. If multiple threads try to extract quadratic factors from the same polynomial at the same time, their mathematical updates collide.
Right.
They create a race condition. They interfere with each other, corrupting the data.
So how do they get around that?
If we connect this to the bigger picture, they use a technique called zero suppression, and it's powered by an adjoint matrix operation.
Okay, help me visualize this adjoint matrix. Because when multiple threads are operating on the same data space, my brain pictures like a single shared Google Doc where multiple people are typing over each other and it just creates total chaos.
That's exactly what computational interference is. Thread A's update corrupts the slope that thread B is trying to calculate.
So does the adjoint matrix act as a mathematical lock? Like noise-canceling headphones?
That is a phenomenal way to describe it. It acts as a highly specialized mathematical filter. When thread A is updating its specific quadratic factor, the adjoint matrix operation computationally filters out the noise or the influence of thread B, thread C, and thread D.
Oh, wow. So thread A only hears its own mathematical feedback. The matrix zeroes out the interference from everyone else without actually having to stop anyone from talking.
Precisely. It isolates one root's influence from another's update vector. That means isolated updates can happen simultaneously. Multiple threads can be ripping quadratic factors out of the polynomial at the exact same time. They don't have to wait in a sequential line, and they don't corrupt each other's data.
That is brilliant, and it bridges us perfectly into the bare metal parallelism section. We've got the algorithms, but how does the code actually utilize the CPU's physical cores without choking on synchronization overhead?
Well, whether we're using the complex Abirth engine or the real number Bairstow engine, we are heavily relying on multi-threading. But running multi-threaded math without crashing a CPU usually requires an immense amount of overhead, specifically mutexes.
Right, mutual exclusion locks. For anyone who hasn't worked with low-level software, a mutex is basically a software traffic light. If thread A needs to write data to memory, the mutex turns red for thread B, forcing it to stop and wait.
Exactly.
But the documentation for ginger-cpp proudly states that its hardware-aware thread pool uses 0 mutex locks. How is it running parallel math without a single traffic light?
By designing the data flow around a concept called Gauss-Seidel data independence. The engineers architected the memory access so that no two threads ever need to write to the same location.
How is that possible if they're solving the same polynomial?
Because of how the data is partitioned. During an iteration step, every single thread reads from a shared poolly old state memory. Reading data simultaneously doesn't cause crashes.
Right, reading is safe.
But when a thread calculates its new vector, its new approximation, it writes that data strictly to a private, isolated memory lane owned only by that specific root.
Here's where it gets really interesting because they are all reading the same communal billboard, but writing in their own totally separate private notebooks. They never actually collide,
Exactly. And because there is zero risk of collision, you don't need the traffic lights. You don't need mutex locks.
which is incredibly rare in software development.
It's a massive performance victory. Mutexes are incredibly slow. When a thread hits a lock, the CPU has to pause, save the thread state, switch context, and invalidate the cache. By achieving Gauss-Seidel data independence, ginger-cpp lets the CPU cores run at absolutely native hardware speed. The computation never stops.
Which leads to a performance paradox that blew my mind. Normally in software, making a problem bigger makes it run worse. There's a theoretical limit governed by Amdahl's law, right?
Yes. Amdahl's law defines the limit of parallel speedup based on the fraction of unparallelizable serial work. Basically, even just the serial code required to boot up the threads and assign them memory will act as a ceiling. Because of that management overhead, no 8-core CPU can ever deliver a perfect 8x speedup.
Right. But the charts in the source deck show something completely counterintuitive. As the polynomials get larger, the scalability actually improves drastically. A degree 100 polynomial scales across the cores significantly better than a degree 20 polynomial. Why?
It comes down to the workload ratio. When you have a massive degree 100 polynomial, the actual mathematical computation required by Horner's method and the Newton steps is so astronomically huge that it completely dwarfs the tiny fixed amount of thread management overhead.
Oh, I see. The time spent beating up the threads becomes a statistical rounding error compared to the time spent crunching the math.
Exactly. The CPU spends almost all its time doing pure, log-free, parallel math and almost zero time managing the architecture. Because of that, at degree 100 on a standard 8-thread CPU, ginger-cpp yields a near optimal, roughly 7.5x speedup.
7.5x on an 8-core machine, that is staggeringly close to the theoretical maximum.
It really is.
And speaking of workloads, there's a domain-specific optimization mentioned in the docs that is just undeniably clever, the autocorrelation hack.
Ah, yes, the Aberthaud-Cormt implementation.
Right. So in domains like time series analysis or signal processing, engineers often deal with autocorrelation functions. And because of the nature of the math, these functions produce highly specific polynomial structures where the roots perfectly mirror each other across the complex unit circle.
We call it reciprocal symmetry. If the complex number z is a root, then 1 over z is guaranteed to also be a root.
And ginger-cpp capitalizes on this natively. Instead of launching a massive swarm of guesses to find all the roots, this specialized function only computes the roots inside the unit circle. Once it finds them, it instantly derives the outside half just by calculating the reciprocals.
Literally having the workload.
Instantly.
And not only are you having the workload, but you are also massively reducing the complexity of the Wilkinson correction.
Oh, right.
Half as many roots means reducing the repulsion wave loops by 50%. It's a stunning example of tailoring the algorithm to the specific realities of the engineering domain.
It really is. But listening to all of this, joint matrix filters, zero suppression, hardware-aware thread pools, specialized autocorrelation routines, it sounds like an absolute nightmare to actually code into a daily workflow. Like, if I'm a software engineer, I just want my roots. I don't want to spend 3 weeks configuring low-level memory alignment.
And that is where the architecture of this library truly shines. You don't have to configure any of it. The true brilliance of ginger-cpp is its zero-friction API. All of this profound complexity is entirely abstracted from the user.
The slide demonstrating this drop-in parallelism is almost funny in how simple it is. To upgrade a serial root finding process to a hardware-optimized parallel architecture, a developer just adds exactly 3 characters to the eighth of the call.
That's it. You just change the function call from a birth to a birth up for multi-threaded.
3 characters. And you instantly unlock the descending order cache prefetching, the dual engine routing, and the Gauss-Seidel lock-free execution. It is mind-blowingly simple.
Is the perfect bridge. On one side, you have the pure, unyielding mathematics of the 1824 Abel-Ruffini theorem forcing us into numerical iteration. On the other side, you have modern, bare metal, multi-core silicon. By marrying the two with such a clean abstraction, ginger-cpp provides a necessary tool for everything from signal processing to quantum mechanics.
It really is a fascinating journey. To summarize, we started from an 1824 mathematical wall that forced humanity into numerical iteration, all the way to a modern C++ library that strips waste with Horner's method, dynamically routes between complex abirth swarms and real Bairstow deflation engines, and utilizes pure Gauss-Seidel data independence to achieve lock-free hardware parallelism.
It represents the perfect synthesis of pure mathematics and bare metal software architecture.
Absolutely. But I want to leave you, the listener, with a final thought to ponder, building on a teaser from the very end of the project's documentation. The sources mention a future state involving GPU acceleration via CUDA and OpenCL.
Oh, yeah, that is going to be massive.
Right. Think about the implications of everything we just discussed. If a standard 8-core CPU can push a 7.5x speed up just by keeping its memory lanes clear and replacing mutexes with mathematical filters, imagine what happens when we unleash the exact same lock-free, mathematically independent algorithms on a GPU with thousands of parallel cores.
It's almost hard to
Right.
fathom.
Are we about to see real-time, massive degree polynomial solving that could fundamentally change how quickly we can simulate quantum environments or process massive neural networks? That 1824 mathematical wall has dictated the limits of computation for a long time. But with architectures like this moving to the GPU, we might be about to pulverize it into dust. Thank you so much for joining us on this deep dive. Keep exploring, and we'll see you next time.